So the next topic to talk about is density. We talked about density before. It's mass divided by volume, and in the metric system, and the system that we use generally, this is grams. Mass is units of grams, and volume is units of centimeters cubed. Now, we also know that you'll often see this is the equivalent of grams per milliliter, because a milliliter is a centimeter cubed. Okay, so they have the same. Their definition is the same. So, having said that, I wanted to also point out to you, people get in the trap of always using the density equation, and this is what I want you to remember. You can do it with dimensional analysis, that's one. And the second thing is the units are telling you what to do to calculate density. You take the mass and you divide by the volume. So, here's a problem. This is a typical kind of lab situation. You have an object with a mass of 17.85 grams, and you take it and you place it in a graduated cylinder containing 50.1 milliliters of water. So basically, the graduated cylinder, hopefully you're familiar with what that looks like. It looks something like that. And it's got 50.1 milliliters in it. And then you take this 17 gram object and you place it in the water, and the volume rises to 63.6 milliliters. And this is actually data, I think, from an experiment that we did in the lab. Then the question is, what's the density of the object? Now, you have two volumes and you have one mass, right? Now, why did the volume go up like that, right? And the answer is because the object, let's say it's a cylinder, right? When you put it in there, displaced water, and that's what created the difference in volume. So the difference in volume is telling you take the difference in volume to get to the volume of the object. So to calculate the volume of the object, we're just going to take 63.3 and subtract 50.1 milliliters, and that's going to give us, let's see, 13.2 milliliters. And then what we're going to do is calculate the density. So how do you do the density, right? Well, the units for density are grams per milliliter or grams per centimeter cubed. And so what we're going to do is we're going to say 17.85 grams divided by 13.2 mLs. And that'll give us the units that we're looking at. This is also a type of dimensional analysis. I know the units for density, so I know how to get to the density. Okay, so then I'm going to pop it into my calculator again. Gosh, you need a calculator so many times for this. And this one I actually don't have the answer on the screen, but it comes out to 1.32 if I remember right. 17.85 divided by 13.2, 1.3. See. Oh, it's 1.35 grams per ml, like that. Yeah, that makes sense. Okay, so again, you could use the density equation, but you notice I didn't use the equation. I just did the equation because I knew what the units were. So it's just a lot easier than having to think, do I have to rearrange this? And stuff like that. Let me show you another example of how you use density. And this is, again, using density as a conversion factor. It's telling us the relationship between mass and volume. So there's a substance, it's called butyl lithium, and it's pyrophoric. So what that means is as soon as it is exposed to air, it catches on fire. There's been a lot of horrible accidents because of that, because it'll leak out as you're trying to use it, and it catches right on fire and burns very violently. But let's say there's an experimental procedure, and it calls for 7.85 grams of liquid N-butyl lithium. And it gives the density. What volume of liquid should be dispensed? Now, again, it catches on fire in air, so you can't actually weigh it on a balance. And so what we typically do is measure its volume and then inject it in a reaction vessel without any air in it. So let's see. I need 7.85 grams, and I need the volume. Now, it doesn't say the units, but what are volume units? Well, centimeter cubed is the volume unit, so I'm going to write that. And you notice this is the conversion between mass and volume. Density is the relationship between mass and volume, so it can be used as a conversion factor for that. I'll start with my given, 7.85 grams, and then I'm just going to multiply it so the units cancel. So it's going to be 0.680 grams and for 1 centimeter cubed. And that's how you would write this part here, right? And you plug that into your calculator, which of course, I've got to go back to this guy. And I'm going to say 7.85, right, divided by 0.680. I'll just leave the 0 off because it is a 0. And that comes to 11.5 centimeters cubed. And the units grams will cancel. And there you go. There you have it. There's the volume. Now, you notice, again, you could have used the density equation. And you know density is equal to mass over volume. So to get the volume, you're going to have to go D times V is equal to M, and then you're going to have to do V is equal to M over D. And I'll tell you what, when you're in a hurry, 90% of the time you'll get that wrong. Okay, I'm not even sure I'm right, but I'm pretty sure I'm right. I'd have to double check. But see all this work that I had to do up here? I didn't do any of that to do this calculation. I just know how to cancel units, and that's how you get to the answer. So make sure you try to do for every problem that you see except for one type, and I'll show you that in a second, to try to do dimensional analysis, because it always works out to be more efficient and easier to find, like when you make a mistake, okay? Saves you a lot of time. This is the type of thing that you can't do by dimensional analysis, and that's when you have an equation, okay? And it's not all equations. Like the density one can certainly be done by dimensional analysis, but that's the temperature conversion is one of those problems where the equation doesn't allow you to directly use like dimensional analysis. So you have to use the equations. Now there's 3 temperature scales which are common, two of which are common in the sciences, but one is common to our everyday experience. The everyday experience is Fahrenheit, okay? The scientific temperature scales are Celsius and Kelvin. And Kelvin, again, is the SI temperature, and Celsius is the metric temperature unit, okay? So it says given, right? And then and a plan. Use equations to convert Celsius first. Use Celsius results to calculate Kelvin. So you're given 98.6 degrees Fahrenheit. That's what you want. This is a question that's up here. It's almost too easy to miss. You want to convert that over to Kelvin, but we're going to do this. If you notice that Fahrenheit's here, right? And Celsius is here. So I need this equation to do that conversion. And then Celsius is here, and then Kelvin is here. So basically, anytime you convert between Fahrenheit and Kelvin, or Kelvin and Fahrenheit, you have to use both of these equations. So the process then, because it's an equation, is you have to rearrange the equation first, right, to get to the variable you want, and then plug the number in. So I'm going to go degrees Fahrenheit minus 32, right? That's going to be 9 over 5 degrees Celsius. And if you're familiar with it this way, 1.8. The reason I do 9 over 5, because that is an exact ratio, and that's to imply the precision in the calculations. We'll talk about that later. And then what I need to do is multiply by 5/8 or 5/9, and so that's going to be degrees Celsius is equal to, and then 5 over 9 times degrees Fahrenheit minus 32. Okay. Now that's essentially dividing by 1.8, 5/9. But we'll go ahead and plug in the number, so 98.6. So we're going to do it like this, 5 over 9 times 98.6 minus 32. And because it's an equation, I often leave the units off because I'm assuming that I match the units. Let me go ahead and do this calculation then. Oops, sorry, dragging it the wrong way. So I'm going to do what's in parentheses of PEMDAS, right? So don't forget that. 98.6 minus 32. 98.6 minus 32. And 32 is an exact number. We'll talk about that later. And then I'm going to multiply that by 5 and divide by 9. And that should come out to be 37 degrees Celsius. So that's your body temperature in metric units. Now, if you want to convert it over to Kelvin, then all you have to do is, as the equation says here, is Kelvin is going to be 37 plus 273.15. And this will come out in Kelvin units. So we're going to go ahead and do that. Again, I'm just going to take this calc. This is actually easier. I'm going to add 273.15 to that. That's 310.15. And when you write Kelvin again, you leave the degree off of it. Okay, so that's how you would, that's kind of like the plan for all Fahrenheit and Celsius and Kelvin calculations. Look to see which equations you have to use, rearrange the equations for the variable, and then go ahead and plug the numbers in and calculate. Now a little bit more about the temperature scale. I just wanted to show you sort of this graphic illustration. So water freezes at, that's what this says, right, 32 degrees Fahrenheit, or 0 degrees Celsius, or 273 degrees Kelvin. Now, the way the Fahrenheit scale is set up is there's exactly 180 degrees between the boiling and freezing of water. Okay. And so this is 180 degrees Fahrenheit between the boiling and the freezing and the boiling of water. In the Celsius scale, which makes way more sense, is there's just 100 degrees Celsius between the freezing and boiling point of water. It just makes more sense to have 100 degrees there, but I don't know. In the old days, like the old days, 1800s, people made their own thermometers and had their own scales for what the kind of things they needed to do. So like brewers who made beer had a temperature scale. You know, you could have any temperature scale. They just created a thermometer and calibrated it. One of the common calibrations was to stick the thermometer in their armpit to get a temperature, and then another calibration was to stick it in freezing seawater and then boiling water. Just things that were commonly available to get two temperatures, and then they used the scale on usually drawn on a piece of paper to tell like what the temperature was by holding the thermometer against the temperature, the piece of paper. One of the things you should notice is that in the Kelvin scale, right, there are also 100 degrees Kelvin, or 100 Kelvin, I shouldn't say degrees Kelvin, 100 Kelvin between the freezing and boiling point of water. So it turns out Kelvin degrees and Celsius degrees are the same. So if you wanted to know the change in degrees Celsius, the change in degrees Kelvin would be exactly the same because the units are the same. On the other hand, if you do that with Fahrenheit, a Fahrenheit degree is 1.8 times smaller than a Celsius or Kelvin degree. All right. Now, there's also something interesting about the Kelvin scale is the term absolute zero. That is theoretically, okay, until recently anyways, the lowest temperature you could reach. Is nothing could be colder than 0 degrees Kelvin. And when we talk about gas laws, we'll sort of come across like why that's the case, okay? And I might also talk a little bit about like how people got below 0 degrees Kelvin, even though that's absolute zero, about 3 or 4 years ago, I think it was now. Maybe it's 5 years ago. It's not that long ago.